All right, so let's talk a little bit about exam two. And kind of the high level idea of exam two is we've got essentially these three main areas: closed systems, control volumes, and the big one, entropy and the second law. So we're going to dive into each one of these. And maybe something to kind of keep in mind is we're not going to talk about every single detail that is going to be on the exam, but just kind of give you a sense of what's going to be there. So you can you can take sort of that 50,000 foot view of everything. All right, so if you think back to closed systems, what was going on there? So we talked a lot about closed systems at the beginning of class, more towards chapter one, two, three, in those sections where we started exploring the first law. But this was very specific around closed systems where we had this container and one of those boundaries on that container was moving. So it's typically this piston looking system. So if we take movable boundary and then we say, all right, my boundary along the outside edge here is fixed, we were then analyzing our first law using the idea that we had our Q in, Q out. We said something like our Q in. We could have other work here, other work in, our heat out, and we could have other work out. And if I removed, I'm just going to go ahead and be a little lazy right here because many of our systems, we said, our change in kinetic energy was zero for the system. Our change in potential energy, the system was zero. So I'm just going to state that up top. So then I can write change in internal energy. And then what we added here was we added plus work at the boundary. So most of the examples that you did, or most of the homework problems that you did, your work terms, your in and out work terms were oftentimes zero. And in many of the cases, one of the heat terms was also zero. So we ended up with a relatively straightforward equation. So then we spent a decent amount of time kind of diving into work at the boundary. So work at the boundary really came down to these conditions. We said, well, you could have constant pressure. So my system would have constant pressure, could have constant volume. I could have polytropic. And I like to think, this is fairly true in most places. I like to think about a subset of polytropic is isothermal. So what happened with each of these cases? Well, nice thing, or at least one of them, is if you have constant volume, what's happening? Well, I have a PV diagram. And if I know that work in the boundary is where we're integrating this pressure over essentially my change in volume, if I don't have a change in volume, I'm not doing any work, right? So in other words, if my volume is constant from state one to state two, I know that my work is zero. There's no area under that curve. So we'll say if I have a constant volume, it's just a darn container. We don't have any moving boundary essentially, or work at that boundary. If I had a constant pressure, you can kind of look at it right here. What happens when we pull that P out of the integral, or we draw it on the picture here, we go from state one to state two, we have just a line across there. Then that means I have just this area under the curve. So my work on the boundary is pressure at either state one or two. Some people just write P0, but that character right there is P1 or P2 because they're the same. Times my change in volume. And then polytropic, that was kind of an oddball. So polytropic was the idea that we had a pressure and volume at state one that's related to pressure and volume at state two. And it's related very specifically through that in right there. That's what makes it polytropic. There's no longer a linear behavior. So we expect something like this. We expect now from state one and two, it could be going down, it could be going up. It could be something like this. Could be going up like this from state one to two. But for sure, we're going to have work on the boundary. So this is the one most people get a little confused with for work at the boundary, is this particular equation. So my work at the boundary for this case would be, you don't need to do the integration on it. You can just use this pre-canned formula, but just recognize that essentially we did some wizardry with this. We ended up with P2 V2 minus P1 V1 divided by 1 minus N. And oftentimes I'm asked, well, what is N? N is a constant, at least we're going to assume that it's constant for our substance. So it's given for us for our particular substance and condition. There was a homework problem where we did have to find N, but in that case you had both your pressure volume on either side. And the last case is that special case of polytropic where N equals 1. And when N equals 1, really what that's saying is that my temperatures are equal to each other. So it's isothermal. And all that means is that now instead of being PV to the N, it's just PV equals PV. So that's what's relating our two states together. And that work at the boundary ends up becoming, I'm not going to go through the derivation, but we end up with C, not a constant, just a term. We replace that C with one of the pressure volume combos. So it could be P1 V1 times the natural log of V2 V1, or you could write it as P2 V2 natural log V2 V1, or you could replace those pressure volumes, I'm sorry, those volumes with pressures, because we know using this relationship, we can put all the pressures on one side. So P1, P2 is equal to V2, V1. So you can interchange, ratios. Do you want pressure ratios, volume ratios? And those are all your work at the boundary formulations. So we only have 3 because one of them is 0 out of all 4 cases. So you can kind of think about, let me put it in a different color here. Let me just kind of highlight it. You can think that the condition that ties the two states together is this. It's either they have the same pressure between state 1 and 2, the same volume, this relationship to each other, so polytropic relationship, or an isothermal relationship. You get an added bonus with the isothermal relationship because you also know T1 is equal to T2. And I know I wrote it over there, but I'm just rewriting it again. So you can think that this work at the boundary idea is telling you essentially how these two states are related to each other. All right. So some other things that we talked about in that particular section was, okay, that's great. I can connect the states together, but what if I don't really know everything that's happening in my particular state? Um, and that's where we started talking about things like, all right, maybe I do have a table, maybe I don't have a table. What if it's an ideal gas? What if it's not an ideal gas? How do I know? Right? So many questions. So this kind of dovetailed from things that we talked about in the previous exam of substance. So the substance idea is what's going on at one of our states. So at state one or at state two. So we first need to identify, do we have a table for it? And by table, really what I'm saying is it water? Can we go to that water table and pick off properties? Or is it R134A? If neither of those things are true, right? If it's not one of those things, but yes, rejoice, right? Because you can go right to the table for your data. If it's not, no, usually it's a little bit of a frowny face. And we say, all right, well, what is the substance? If it's air, we have some table for that. But before we get to there, we should say, no, is it a gas? A gas. There we go. That's a better intermediate. No, we'll say, is it a solid? Right? And then we start thinking about, um, is it a fluid? So if it was a solid, we'd be in a materials problem. Is it a fluid? Right? So what state is it in? Or hopefully, yes, it's a gas. And then we can say, is it air? So if it's air, the nice thing is we've got a table for that, right? Or organized by temperatures. And if you don't remember, be sure to go back and review um, the whole idea about the, it's a gross color there, relative pressure and relative volume. We'll come back to that in a minute. Just kind of nice to note that right now. Those are only valid when you have an isentropic condition. That's the only time we'll use those. But we can use those air table generally for things like U's and H's. If it's not air, maybe we panic a little bit. And we think, all right, well, what is it then? Some kind of substance, but we know it's a gas. So is it ideal? So we're going to check ideal by looking at the compressibility. So going to that chart and figuring out Z. ZRT. There we go. And that's no. This would be yes. Z is 1. Life's good. Right? It just becomes RT. So kind of alongside that, I'm just going to draw it weird because you all need to do a concept map so you can put the pieces together. We talked about this idea of constant specific heat. I'll call that, and variable specific heat. So when we talked about constant specific heat, for the closed system in particular, we'll say that that really came out of finding our delta U's and delta H's, so internal energy and enthalpy. And we said, all right, well, constant specific heat is the idea where we had delta U, and we could say, we can pull out that CV and say specific volume, I'm sorry, specific heat, CV, average at that temperature. I'll write average here, times delta T would give you your internal energy. Likewise, for enthalpy, we had Cp, that's a little c, not a big C. Kind of hard to tell. There we go. There we go. And it's really average. A lot of times we drop that subscript times delta T. When we were talking about variable, what that really meant is we were integrating between our two states. What we often did is we used a table. We said U2 minus U1. So when you say variable specific heat and you do that subtraction with your table data, whether it's the air table, the R134A table, or the water table, you're implying variable specific heat. And same thing's true for delta H. Right? So something like this. Now, let's talk about our good friend control volumes. Zoom out here, zoom back in. So one of the big things in control volumes that we added was the idea of conservation of mass. And so we said, really, what that meant was mass in minus mass out equals our mass that gets stored in our control volume. For steady state, we made the assumption that mass in is mass out. And that could be mass, just like that, could be m dot. So rate, mass flow rate. And the other thing that we did, we started talking about specific devices. And I'm not going to go through here and detail all the devices, but I will kind of start out with the generalized first law, so that you can go back and maybe see those things again in a different light. So we said first law applied to these different devices is Q dot W dot, and then we connected U plus work on the fluid into H, so it became H dot. We had kinetic energy, potential energy, and I'm just going to say that's energy. Be a little lazy here in writing. We can say energy in, energy out. Those two terms are the same. And as we've talked about, steady state for the system, typically all of our systems in this class, that right side zeroes out. So we end up basically manipulating these terms. And a form that we used pretty frequently, I'll write a different color, I'll write it red, a little more important, was we said Q dot, we left that. Sometimes we had other work. Maybe it was a resistor in the tank or something of the sort. But we did often say m dot times little h. I'll write a version of that in just a second. And we pulled the mass, and one could say the dot, out of the kinetic energy and potential energy. So where, let's take the easy ones first. Kinetic energy is 1/2 velocity squared. And potential energy is GH. Just for some things to note, kind of confuses people. With the m dot h action there, you can say, how do I connect this with that term? And we can say, all right, well, H is specific enthalpy. We could do it for Q as well, or work. So heat and work. I'll write those forms. The idea is you could say, well, what is specific enthalpy? It is enthalpy divided by mass. Or another way to write that is H dot m dot. And you can do the same thing for Q, right? Big Q divided by mass is specific heat transfer. Q dot m dot. So work or mass for specific work, or we can say power, so W dot divided by m dot. And that's how we developed all those handy dandy equations for devices. So mixing chambers, and we assumed that the pressure was equal. We talked about things like nozzles and turbines, right? And we came up with very specific equations. I'm not going to write all those out, but what we tended to do is focus in on essentially our enthalpy m dots in, enthalpy m dots out. And there were variations of the devices. Some devices had kinetic energy, like a nozzle. Many did not. Most did not have potential energy, right? They usually had, that's a terrible color. Most systems dealt with something like kinetic energy, power, heat, or H. Generally not potential energy term. It could, but generally didn't. And that was our control volume section. It actually felt a lot lighter than our closed system stuff, right? And then we got to the big topic, enthalpy. Entropy, not to be confused with enthalpy. So not going back through the idea of what is entropy. You should definitely revisit that. But one of the main things that we talked about was the idea of processes occurring in a certain direction. And I'll write these down here. I don't want you to forget these. Entropy is not conserved. It's not a conserved quantity. Even if we balance it, it does not imply it's conserved. And we spent a decent amount of time in that entropy section figuring out what entropy was. And in a nutshell, what we talked about was, well, I've got this larger system boundary. I'm going to talk about an isolated system. And within that, I could have a device. I could have a turbine. I could have a whole bunch of devices, right? And I'm just going to draw some random devices. check valve, I don't know, making stuff up, right? So the concept here is that each one of these devices can have their own entropy, right? So their own delta S. So we can take the sum of those delta S's for each device. Let's try that again. So n number of devices, and all of the heat going into the surroundings. So we could have something that's confusing is this device might be in one surrounding or it might be in multiple surroundings. So for example, your heat pump for your home, you have that big box that sits outside that's exchanging heat with the outside air, and you have a box inside your house which is exchanging heat with inside air, right? Totally different temperatures of surroundings. Surrounding one, surrounding two, but it might be in this little box. So we're adding that depending on the direction of Q, that little heat over temperature surrounding. I'll call it Q1. And that's our entropy that's generated. We'll stay careful with the signs. And what we found from second law is that entropy generated must always be positive. So we're never going to decrease our entropy. Now we can have decrease, the device could decrease entropy, but the overall system is not going to have a decrease in entropy. And we talked about some scenarios where we said, all right, well, we drew these little clouds, and we talked about a heat engine, a heat pump, and basically a refrigerator. And our heat engine basically took our high temperature reservoir, transferred heat to our device, and we peeled off a little bit of that into work. We could also put dots above these things if you wanted to do that. And we dumped that into the low temperature reservoir, QL, QH. And the heat pump, like its name implies, if we want to reverse that, we need to put work in, QH, QL. Same, the refrigerator. Just that we thought about the efficiency a little bit different. These could be dotted as well. Dots or no dots. Depends on what you want. This could be power, it could be work. We talked about thermal efficiency for the heat engine. And we said, well, I don't, my thermal efficiency doesn't totally make sense for the heat pump and the refrigerator. So I'm going to talk about something called COP, coefficient of performance, for each of those cases. And for the refrigerator, there's a whole bunch of different forms of this. So be sure to go back to it. We said QL over work in. For the heat pump, what do we want? We want the QH. So it'd be QH over work in. And thermal efficiency for the heat engine, what do we want? Well, we want work. We say work out over what's needed to make that happen, heat in. And recognize that we said, oh, okay, we have Carnot, that just implies ideal. And we're going to say that if it's reversible, ideal, reversible, then we can take our ratios of heat to temperature. But that's only for Carnot. And this is the best we can do. We're still going to generate entropy. We're not going to get away from that. So we've got, right, we've got heat going into surroundings. Okay. I'm going to kind of migrate it into a more specific conversation on entropy. We said, okay, well, really, more specifically, if something's reversible, we're really saying that entropy on that device is zero. It's ideal. A reversible, ideal, right? We're kind of using these all in the same way. And then how do you find, well, that's great, reversible, delta S is zero. But how do you generally find delta S? So kind of like what we talked about with pure substances above, when you're finding your internal energy, right, up here, we said, well, kind of depends on if you know your substance. If you know that it's R134A or water, guess what? You can look up S1 and S2 from your tables. Yay! Which implies variable specific heat. You think that that's exact analysis. Not exact, but pretty darn close, right? We'll say really good analysis. If it's not those things, if it's not in the table, we have a case for error. So if you're finding delta S for air, we could say, okay, well, that's great. I've got a table, but it's relative. I can use this. There's another form of this equation. I'm just going to leave this form for simplicity right now. Or if you knew that, yeah, my temperature range is pretty small, and I need to just approximate this, you could approximate or constant specific heat's what that means. You could say that your delta S would be Cp natural log T2 T1 minus R natural log your pressures. Again, there's another form of that equation. If it's not air, you panic a little bit. You hope that it's a noble gas. Noble gas? It's a noble gas, then you know constant specific heat is pretty much equal to variable specific heat. Therefore, it works really well to use that equation above. If it's not a noble gas, we know that this is going to be an estimate because we're going to use that constant specific heat equation. So the delta S CP. Okay, just stop writing it. I'm getting tired of writing that. But we know that this is an approximate now. And it's true that we do have tables for some different substances, but not for us in this class. And we did some other kind of, I'll say wizardry, but what might feel a little bit like trickiness, where we essentially played around with isentropic. So what is isentropic relationships? We said isentropic is just same, so ice without the O, entropic, so entropy, the same entropy. So what that meant was delta S was 0. If we were using tables and we only had two states, so example, only two states, and we were using tables, this was typically handy because we could say things like S1 and S2. And just remember, if I have a device that has multiple outlets, for example, and it's isentropic device, the entropy here is equal to the entropy at the end. It is not this. Don't do that. That would assume entropy is conserved. It's not true. If you didn't have the tables, what we did was we just took these formulas and we set the left side equal to 0. So if you're dealing with air, you ended up with a form that we manipulated it, basically. Or we took this one, set that equal to 0 for the constant specific heat equation. Or it's actually variable specific heat for noble gas. And depending on what you solve for, change how this equation looks. And we said for air, one of the neat things that we can do, if it's isentropic, is there's actually a set of data in the table with the R subscript. And let's do that, where we can say, what I was writing above, P2, P1, P2R, P1R. Just remember, this is only for the case of it being isentropic. You can only use this ratio when that's true. V2, V1, V2R, V1R. In a different form of this, sorry, use table, A17 or A17E. Different form of this constant specific heat. Ideal gases, should make that note, right? I'll recast them for you so you don't have to play around with the equation here. P2, P1, K minus 1 over K. Or you can put it as a volume ratio. Or just do some algebra. And you have that form. All right. Well, I'll also share, I don't know if it's helpful to share all these notes. You're more than welcome to have them, so I'll add them in Canvas as well. Just try to make the connections for yourself as you go back and study some of the problems. And just something else to remember is it's easy if you know which section you're in. It's really hard if you just start a problem and you don't actually know what the problem is, control volume, closed system. So try to get good at identifying what you're dealing with. All right. Well, thanks for listening.